Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
Imagine you have 50 pieces of information, like the test scores from 50 students, floating around in your computer's memory. Right now, they're disconnected. Every single score is essentially bouncing around in a chaotic, disorganized cloud. If your computer needs to process those scores quickly, this chaos is a disaster. It has no way of predicting where any specific piece of data is located, which means it wastes time hunting them down one by one. To fix this, programmers use a structural tool called a one-dimensional array. You can think of an array as a long, organized digital locker. Instead of letting those 50 scores float freely, the array forces them into a single connected row of slots. This locker comes with two strict ground rules. The first rule is contiguous memory. This means the array takes up an unbroken block of space, and every single slot has to hold the exact same type of data. The items sit perfectly shoulder to shoulder, with no empty gaps in between. The second rule is zero-based indexing. The computer assigns a numerical address to every slot, so it knows exactly where to look. But in programming, counting always begins with 0, not 1. Because of this zero-based counting, the address for the very last slot in your locker is always the total number of items minus 1. So in our array of 50 scores, the final item sits at index 49. By putting our data into this array, we have given it a permanent, predictable home. We know exactly where the group begins and ends, which finally makes it possible to manage large amounts of information. But we still have a bottleneck. Our data is securely stored, yes, but what if you're looking for the absolute lowest score in the group? If those 50 scores were placed in the array randomly, finding the lowest one means checking every single slot, one by one. It is exactly like trying to find a specific novel in a massive library, where the books are just thrown onto the shelves at random. You would have to look at the first book, then the second, then the third, constantly trying to remember which one was the closest match to what you need. It takes an agonizing amount of time. Now, imagine that same library was perfectly organized in alphabetical order. If you need a book by an author whose last name starts with W, you can instantly skip 95% of the building and go straight to the end of the alphabet. In the digital world, we create this kind of predictability through sorting. Sorting is the algorithmic arrangement of chaotic data into a strict ascending or descending order. It is the critical step that turns a slow, exhaustive search into an incredibly fast, targeted operation. So how does a computer actually organize a messy array? Under the hood, it creates this order by playing a repetitive game of compare and swap. One famous method is bubble sort. The computer compares two adjacent items. If the left item is larger, they swap places. Doing this repeatedly down the line, the heaviest elements slowly sink to the array's right side, while lighter elements bubble left. If we look at this Python code showing a bubble sort in action, we can see how the computer executes this. The code checks if the current item is larger than the one right next to it, and if it is, they trade positions. It is an easy method to write, but because it relies on thousands of tiny individual swaps, it is notoriously slow. We can try a completely different strategy. Imagine a coach walking down a messy line of athletes. Instead of shuffling people around, the coach scans the entire group before taking action. This is called selection sort. The computer scouts the entire remaining array to find the absolute minimum value, and then pulls it directly to the front in one big jump. Selection sort saves energy by making far fewer physical swaps than bubble sort. However, it still pays a heavy time penalty because it has to repetitively scan the whole unsorted line to find every single lowest value. Our third classic strategy is probably the most natural to humans. It is exactly how you organize a hand of playing cards. When you pick up a newly drawn playing card, you naturally slide it right into its proper sequence. Computers do this with insertion sort. It takes a new item and carefully slides it into an already sorted section by scooting the larger elements out of the way. Insertion sort is incredibly fast and efficient, but it comes with a catch. It only hits top speed if your array is already mostly sorted. Think back to those 50 chaotic variables floating around. Now look at them. They are locked into a connected line, starting at index 0, perfectly ordered from smallest to largest. When you give data strict physical structure through arrays and mathematical order through sorting, you give the computer exactly what it needs to process complex information at lightning speed.
Have you ever wondered how your phone merges duplicate contacts so quickly? Or how massive databases prevent duplicate user accounts from literally crashing their entire system? Welcome to this step-by-step explainer. I'm really glad you're here. Today, we're going to completely demystify a foundational computer science concept, finding duplicates in arrays. We're going to take this at a nice calm pace, so sit back, focus on the logic with me, and let's build this solution from the ground up together.
Okay, let's dive into this. We are using a simple three-act method today. First, defining the problem. Second, designing the algorithm. And third, walking through a dry run and the actual code.
Part 1. Defining the problem and why we prioritize logic over syntax. Before you even touch a keyboard or think about typing a single semicolon, I want you to internalize this core mantra. Logic is the same everywhere, just syntax changes. Say it with me in your head. Logic is the same everywhere. Whether you're coding in C, Java, or Python, the underlying human thought process required to solve a problem remains identical. The computer is just a machine waiting for your highly specific instructions, right? Master the logic first, and the syntax becomes almost effortless.
So, what exactly are we looking for here? Well, a duplicate is simply any number that appears more than once in a collection. Think about a massive database of user IDs or financial transactions. Finding and handling duplicates is absolutely crucial to prevent corrupt data or system crashes. In programming, an array stores these elements right next to each other in contiguous memory. Our mission is to hunt down any identical twins hiding within those memory blocks and to do it efficiently.
And this brilliantly illustrates the two totally different paths we can take to find that duplicate. First, you've got the brute force method. Imagine trying to find a matching pair of socks by picking one up and blindly comparing it to every single other sock in a huge laundry pile. You grab the first number and check it against literally the entire rest of the array. It takes a tremendous amount of time and processing power. Instead, we're going to use the sorting method. It's like organizing that laundry first. By sorting the array, we force identical numbers to sit right next to each other as adjacent neighbors. So instead of searching the whole pile, we just check the item right next door. A real game changer.
Part 2. Designing a clean sorting algorithm. And remember, we are still holding off on code to focus purely on human logic.
All right, here are our algorithmic steps laid out in plain English. Step 1, we sort the array in ascending order. Step 2, we loop through the array, starting at index 0. Now pay very close attention to this next part. We only loop up to the array's length minus 2. Why is that specific boundary so absolutely critical? Well, because in step 3, we are comparing our current element with its neighbor to the right. If our loop went all the way to the very last element, there wouldn't be a neighbor to check. The computer would try to access memory that frankly doesn't exist, leading to a fatal array index out of bounds error. Finally, step 4. If the current element and its neighbor match, boom, a duplicate is found without having to search the entire pile twice.
Part 3. Dry run and code. Let's visually simulate how a computer's memory processes our logic step by step.
Now, what's really interesting about this slide is that we get to act as the computer. Let's trace this logic flow matrix for an unsorted input array of 4, 5, 1, 3, 1 to prove this works flawlessly. Step 1 is our initial sorting step. The array magically transforms into 1, 1, 3, 4, 5. Okay, next we begin our loop at index 0. The current element is 1. We look exactly one step to the right at its neighbor at index 1, which is also 1. The computer evaluates the condition. Does 1 equal 1? Yes, absolutely true. A duplicate is found immediately. The algorithm returns 1, and we are totally done. Notice how much processing power we just saved. We didn't even have to look at the 3, the 4, or the 5.
So the crucial point here is how beautifully simple it is to write the code once the logic is fully understood. This generic pseudocode right here isn't tied to any specific language, which reinforces our core mantra: logic is the same everywhere. We define a function, we sort the array, we create a for loop stopping right before the very end, and if the current element equals the next element, we print and return it. Honestly, the code is quite literally just reading our plain English logic back to us. Because we solved the problem logically first, the syntax practically writes itself.
Knowing that logic is the same everywhere, how would you write this exact algorithm using the syntax of C, Java, or Python? That is my challenge to you today. You have the blueprint. You understand exactly how this works under the hood. So go open your code editor and try translating this universal logic using something like qsort in C, arrays.sort in Java, or just a simple sort function in Python. I bet you can do it in under 5 minutes. Keep exploring the logic behind the code, and I'll catch you in the next explainer.
Now let's see how the code looks in C. in Java. In Python. Let's now move to the second one.
Welcome to the explainer. I want you to take a deep breath, clear your mind, and really focus with me for a few minutes. Today, we're diving into a masterclass on algorithmic thinking. We're not just going to sit here and memorize lines of code. No, we're going to learn how a computer actually processes information at its core. So let's just jump right in.
Now, the absolute anchor for today is this quote right here. Logic is the same everywhere, just syntax changes. I really want you to internalize that. Today, we're completely stripping away all the fluff. We aren't getting bogged down in whether a language uses curly braces or semicolons or specific indentation rules. Instead, we're focusing purely on the underlying logic. We're looking at the universal, step-by-step reasoning that a machine uses to think. Because look, once you master that fundamental logic, the actual programming language you use to write it, well, that's just a minor detail.
Part 1. Defining the array problem. Let's slowly unpack this definition. It's deeply rooted in how fundamental languages like C manage memory. An array isn't just some random list of items. It's a grouping of contiguous, meaning perfectly side-by-side, memory segments. All the elements inside share the exact same name and the exact same data type. But here is the absolutely critical part you have to remember. They are accessed by a zero-based index number. When you start counting in an array, you do not start at 1, you start at 0. Forgetting this is what leads to that classic, incredibly frustrating off-by-1 error, where your entire program just crashes or loses data, simply because you tried to access a position that literally doesn't exist. And you can see how this physically looks in the computer's memory right here. Notice that discrete block of consecutive slots. We have an array named A, and the very first slot is A sub 0, followed right after by A sub 1, and so on down the line. It's exactly like a row of mailboxes on a street.
If you know the base address of the street and the zero-based index of the specific box you want, you can instantly pinpoint its exact physical location in the hardware. So, knowing that our data is lined up perfectly in these contiguous slots, it begs the question, how do we actually find a specific element hidden within this block? Think about it. If I give you a massive row of, say, 10,000 mailboxes and ask you to find the one box containing a specific letter, how do you logically instruct a literal machine, step by step, to find it without missing it or, worse, crashing the whole system? This brings us to part 2, designing a clean search algorithm. Here is our clean, step-by-step algorithm in plain English. Step 1, we start our search at index 0, the absolute beginning of the array. Step 2, we look inside that memory slot and compare the element to our target value. Step 3, if it's an exact match, we stop searching and instantly break out of our loop. And step 4, if it's not a match, we simply increment our index by 1, move to the very next mailbox in the row, and repeat the process. It's a highly systematic, highly repetitive checklist. Now I want you to pay very special attention to step 3. The raw power of the break statement really cannot be overstated here. When your program hits a break, it terminates the loop entirely. Think about why that matters. If you're searching an array of 1 million items and you happen to find your target right away at index 2, it would be a massive, completely unnecessary waste of processing power to check the remaining 999,997 slots. Using break immediately stops the search. It just proves that good, clean logic isn't just about getting the right answer, it's about getting it efficiently. Part 3. The logic flow and the dry run. This visual perfectly illustrates what we discussed at the very beginning of the explainer. On the left side, you're looking at a C program using a for loop to iterate through the array. It's packed with curly braces and parentheses. On the right side, you see a Python program doing the exact same thing, but it uses a while loop and relies heavily on indentation. Visually, the syntax is wildly different, but trace the actual logic with me. Start at an index, check if the value at that index matches your target, and if it does, trigger the break command. The underlying algorithm is 100% identical. The logic is exactly the same everywhere. Let's actually trace this out by doing a quick dry run. Imagine we have an array with the numbers 15, 7, 27, and 39. Our target number, the one we want to find, is 27. Okay, step 1. The computer sets the index x to 0. It checks the value at index 0, which is 15. Is 15 equal to 27? No. So it increments the index by 1. Step 2. The index is now 1. It checks the value at index 1, which is 7. Is 7 equal to 27? Still no. It increments the index again. Step 3. The index is now 2. It checks the value at index 2, which is 27. Is 27 equal to 27? Yes! A match is found, and the computer instantly executes that break command, terminating the search early. And here is the actual working Python script from our source material. You can clearly see that dry run we just did mapped directly onto the syntax. We define our list L, we ask for the target P, and we set our index x to 0. That while loop runs as long as our index is less than the total length of the array. Inside, if L sub x equals P, we hit the break. If you look closely at the very end of the script, after the loop breaks, the program simply checks if our index, x, is less than the total length of the list. That confirms we successfully found the item before running out of slots, and it prints the exact position. So we've built a beautiful, robust search algorithm today, but I want to leave you with one final provocative thought. We know exactly what happens when the logic successfully finds the target, but what happens to the logic if the target value simply isn't inside the array at all? How does the computer know when to finally give up? And what does that final index look like when it does? I want you to keep thinking computationally, keep questioning those edge cases. Thanks for watching, and I'll see you in the next explainer.
Now let's see how the code looks in C. in Java. In Python. Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes.
Well,
Thank you for watching. See you in the next video.
Subscribe now.